All right, guys, so we talked about this last week, Coulombs Law. So we're on page 41 in your notebook, okay? And let's review. Coulombs Law is a law that says F equals K Q1 Q2 divided by D squared. And what this is telling us is that the electrostatic force is equal to a constant times charge 1 times charge 2 divided by the square of the distance. So remember, F stands for force. The two Q's are charge. D is distance. And K is Coulomb's constant. Okay, so let's review. F is measured in newtons. Right, force is measured in newtons. Q is new. Both Q's are charge. They are measured in something called coulombs. The symbol for that is a capital C, measured in coulombs. Coulomb is the unit of charge. So, coulomb is the unit of charge. Of course, distance needs to be measured in meters. And K is a constant. Now, so a constant is a number that we use to make the formula work out to have the right units. Okay, so the Coulomb's constant is 8.99 times 10 to the 9th newtons times meters squared divided by Coulomb squared. So if you would please take a moment and write this into your formula cards. Everybody get out your formula card and write this in. Okay. Everyone should have had an opportunity now to write this into their formula card. If not, just pause the video for another few seconds. Everybody write it down, and then we're going to move on. Okay, so before we just start plugging in numbers, let's go back and look at this relationship, okay? So F is proportional, or F equals K Q1 Q2. So Q is on the top with F, right? So that's what we call a direct proportion. So force is directly proportional that's horrible writing, to charge. So what does that mean? That means if we do a little table, F and Q. So let's imagine what happens to the Q. Or, I'm sorry, when we do something to the Q, let's imagine what happens to the F. So when the Q's are both 1, we just have F. What if I double this Q? And I keep this one the same. I keep this one as a 1. Well, the same factor has to happen to F. So this will become 2F. What if I keep this one the same and I triple this one? Right? 3F, because whatever factor happens to charge must also happen to force. What if I do both at the same time? This Q is doubled, this Q is tripled. They both have an effect. 2 times 3, 6F. What if I make the Q smaller? What if I cut this one in half, leaving this one by itself, or the same? Then I get F over 2. What if I leave this one the same and cut this one in a third? Then I get F over 3. What if I do both? Then I get F over 6. Directly proportional. Whatever happens to charge must also happen to force. Now, what about distance? What about the distance? F is inversely related to the square of the distance. To the square of the distance. So if I make the same table, f and d squared, let's predict what will happen. Now, inversely proportional means that when one term goes up, the other term goes down. We know that has to be true, as we saw here. Distance is on the bottom of this equation. So when this number gets bigger, if this number gets bigger, then this number has to get smaller. If this number gets smaller, then this number has to get bigger. They have to go opposite of each other. Okay? So, back to our little table over here. Let's make our prediction. If I double the distance, two times the distance, what should happen to f? You may be tempted to say, oh, f will get 2 times smaller. But the problem is this distance is squared. So f can't get 2 times smaller. It has to get 2 squared times smaller. So we would write f over 2 squared. Well, what is 2 squared? F over 4. 2 squared is 4. Let's do another one. Let's say we made it 5 times bigger in the distance. So we separate the two objects 5 times larger than they were. Then we would write f over 5 squared, which is f over 25. So far, so good? That's what happens when distance gets big. What happens when we make distance smaller? Let's say we cut distance to 1/4. Now, the trick here is that when you make distance smaller, you're bringing the objects closer together. They were like this, and now they're going to be like this. Well, you know the force has to get stronger. You know it does. So, we know it's going to get bigger. We're going to multiply instead of divide, is how we should think of it. But it's not a factor of 4, it's a factor of 4 squared. So, it's going to become 4 squared times f, which of course is 16f. Whatever the f happens to be. What if I make it 1 over 10? What if I make it 10 times closer together? Then it's 10 squared f, which is 100f. Now, where things get really tricky is when both things are happening at the same time. So, let's zoom out, give ourselves some more space, and let's look at an example of that. What if I think of each thing as happening at the same time? We'll do one example. So I'm going to double the q, I'm going to triple this q, and I'm going to bring the distance, I'm going to make the distance smaller. I'll make the distance smaller by 1/4, or 4 times smaller. So so what does that do to f? Well, it's going to be 2f times 3 for each of these times, that's a factor of 4 squared. So you're going to have 4 squared, so it's 4 times 4 times 3 times 2, which is 96. So this time the force would get 96 times bigger. They each play a role. What if we made this one 3, this one 4, and we did this one, we made it also bigger by 2? Well, then we would have 3 times 4 times, it's getting smaller, so it's f over 2 squared, like that. Well, 2 squared is 4, so this would become 3 times 4 times f over 4. So the 4's will cancel, so 3f would be left behind. They each play their role. Okay? That is the inverse square proportion. Now we're going to look at solving some actual problems. So I'm going to take a moment and get set up. And I want you to copy the question into your notes at the end of page 41. You should have room for 2 questions and then carry over onto 40 with the other 2 questions. We're going to work 4 questions in total. All right, so as I put in this text box, I want you guys to be writing it on your journal pages. Okay. All right, so the question said, find the force between charges of 10C and negative 50C located 20 centimeters apart. And like any and all physics-related problems, I should start with a sketch and a list of my givens. Okay, start with a sketch and a list of the givens. So, I can imagine I've got 2 charges. So here's charge number 1. And it has 10 coulombs. And here's charge number 2. And it has negative 50 coulombs. And the distance between them is 20 centimeters. And what am I asked to find? The force. So there I've drawn a picture and I've listed givens. So this whole lesson has been about Coulombs Law. Now, before we do that, we need to double check our units. Coulombs for charge is fine, but centimeters for distance is not fine. We need to put that into meters. Well, centi means 1/100th. So that means I move the decimal 1, 2 to turn that from centimeters into meters. So this is 0.20 meters. That will matter quite a bit. Now, after we've identified our givens, we're going to plug it into our equation. This whole lesson has been about Coulombs Law. So F equals K Q1 Q2 over D squared. We'll plug in the numbers we know. F equals K is 8.99 times 10 to the 9th. That's our constant. We wrote it down earlier. It doesn't change. Q1 is positive 10, so we just write 10, times Q2 is negative 50, divided by 0.20 squared. Notice the square is on the bottom. So when we type this in the calculator, we're going to use our menu, our math menu, so that we can set up our fraction. Okay? So everybody take a moment, type it in their calculator. Remember, use your alpha key and then hit F1 so that you can pull up your fraction bar. And then for the scientific notation here, use second, and then the little double E key. That way you can do scientific notation. Okay? So I'll give everybody a moment to do that. F equals you should be typing. Everyone should be typing. Compare with your partner. Make sure that you've looked at your exponent carefully. Make sure you've paid attention to converting your units. If you put 20 on the bottom, you're going to be off by 4 decimal places in your final answer. Still waiting on people to type it in and show their partners. All right, if people are still waiting, go ahead and pause it. Otherwise, I'm going to move on in 5, 4, 3, 2, 1. Okay, your force should be 1.12 times 10 to the 14th power. We had all the right units, coulombs and meters. We used the Coulomb constant, so our force is newtons. Now, notice, the sign should be what? We had a positive times a negative. The sign should be negative. Negative 1.12. Because, why is it negative? Well, obviously the math says we had a negative, but also we had opposite charges. So this force is attractive. Opposites attract. When we have opposite charges, the force will be a negative sign. When we have the same charges, the force will be a positive sign. All right, let's do another one. Before we do another one, let's talk about charge. That number is big, to the 14th power. Why is that number so big? Well, it turns out the Coulomb is a really large amount of charge. Okay, a large amount of charge. So, what's a more reasonable or a more common unit of charge is the microcoulomb. Let's talk about microcoulomb for a second. The symbol looks like this, or sometimes more traditionally like a U. This stands for microcoulomb. You should hopefully remember micro from your metric system. So just like kilo is 10 to the third, right? Kilo is 1,000, so 10 to the 3. Mega means million, so 10 to the 6. Milli is 1,000th, so 10 to the minus 3. Micro is like a million in the other direction. It's 10 to the minus 6. So when we see a number of coulombs, if we see microcoulombs, then when we do the problem in our formula, we want to put 10 to the minus 6 on it. We want to replace that micro with the 10 to the minus 6 so we can work the problem the same way we work any other problem. So, that being the case, let's look at another example. All right, so here's the next problem. Sphere A is located to the right of sphere B. Okay, the charge on sphere A is 6.0 microcoulombs. The charge on sphere B is negative 3.0 microcoulombs. If they are separated by 4.0 centimeters, what is the electric force between them? Okay. All right, so everybody should hopefully be able to see that now. Okay, so we're going to draw the picture here. So we have sphere, now notice it says sphere A was to the right, so this is sphere B, and this will be sphere A. And this will be the 4 centimeters. Now, we can't use centimeters, or we don't want to use centimeters. We need to use meters, so how do we do that? Centi means 100th, so we move the decimal 2 places to the left. 1, 2. So this is 0.04 centimeters. Okay? Now, the other thing is the charges, right? B has a charge of negative 3 microcoulombs. A has a charge of 6 microcoulombs. Remember, when we use micro, we replace that with the 10 to the minus 6. Micro was 10 to the minus 6. So, we'll come over here. When we use it in our formula, this should be negative 3 So this should be negative 3 times 10 to the minus 6, and this one should be positive 6 times 10 to the minus 6. Okay, so like everything we've been doing so far in this lesson, it's a Coulombs Law problem. So we'll jump over here and we'll solve the problem. F equals K Q1 Q2 divided by D squared. Again, we don't need to rearrange anything. We have everything okay, we don't need to rearrange anything, so we'll just plug in the numbers that we have. Okay, so F equals 8.99 times 10 to the 9th. This time we're going to use our microcoulombs. So, negative 3.0 times 10 to the minus 6. And 6.0 times 10 to the minus 6. All divided by 0.04 squared. Just like we did earlier, I want everybody to type it in their calculator, compare with your partners. Again, I'm giving you time to type it in and compare with your partners. Everybody should be typing. All right, moving on in 5, 4, 3, 2, 1. So negative 101, and that's where we're going to cut it off. We're going to go to 3 digits. The unit should be newtons. Okay? It's just the same as the other problem, only now we had some more scientific notation. Okay, and both of these examples, we looked at solving for force when we were given charge and distance. The next question we want to be able to do is solve for charge. Okay, we want to be able to solve for charge. So, Let's do that. So, two spheres with identical charges are 75 centimeters apart. If the force between them is 30 newtons, what is the magnitude on each charge? Okay, so how are we going to approach this problem? Well, like we've approached every problem. We've got two charges. We know that they're separated by a distance, 75 centimeters. With the decimal 1, 2, that's 0.75 meters. We know that there's a force between them, okay? And this force is repulsive because it's a positive term. It's 30 newtons. And what are we asked to find? We're asked to find Q. Now, you may be thinking to yourself, which Q? Q1, Q2? What's the deal? But it says that they are identical. So we know that Q1, as far as we're concerned, Q1 is the same as Q2. As far as Coulombs law is concerned, they're the same. Okay? So, what does that make Coulombs law look like? That makes Coulombs law look like this. F equals K, Q times Q divided by D squared. Well, what does Q times Q simplify into? Correct. F equals KQ squared over D squared. So we're looking for that Q, so we'll do a little rearranging. We'll multiply by D squared divided by K, because that will cancel here, and it will cancel here. Well, whatever I do to one side, do to the other. So multiply by D squared over K. Now, we'll clean it up a little bit. We have this Q here, and it's Q squared, so then I've got to square root it, because if I want Q by itself, I've got to square root it. So now, ultimately, what I've done is I've said Q equals the square root of D squared times F divided by K. That's all inside the square root. Well, okay, we know all these terms, we can plug it in. The distance is 0.75 squared times the F was 30 newtons divided by the K is 8.99 times 10 to the 9th power. All of this equals Q. All right, I'm going to give everybody a few minutes. Type it in your calculator. You should be typing. And you should be typing. And you should be typing. You should now be checking with your partner. You should be double checking with your partner. I'll go over the answer in 5, 4, 3, 2, 1. Okay, you should have gotten, and we're going to round our answer to 3 significant digits. Q equals 4.33 times 10 to the minus 5th. The unit should be coulombs. That is the value of the charge on each one of those objects. Okay? All right. Got one more example type to show you. We've used Coulombs law to solve for Q. We've used Coulombs law to solve for force. Now we're going to use Coulombs law to solve for distance. Okay, so again, you should be typing this, I'm sorry, solving this along with us. Okay. What is the distance between two spheres with charge 2.5 microcoulombs when the force between them is half a Newton? Okay, so we've got a situation where we have two objects. They're each 2.5 microcoulombs. Okay, the distance is unknown, and the force is a half Newton. We're going to solve this exactly the same way as we've done. Exactly the same way as we've done. So, what we need to do is rearrange Coulombs Law and then plug in the numbers that we have. Okay, so remember, Coulombs Law, F equals K Q1 Q2 divided by D squared. We're going to rearrange it for D. Well, that's actually relatively simple. I want to get rid of D squared on the bottom, so I'm going to multiply by D squared so that it cancels. Whatever I did on one side, I got to do the other, so I'll multiply this side by D squared. Now that moved the D, but I still have this F in the way. So now I will divide by F because I want it to cancel. So now I'm left with D squared equals K Q1 Q2 over F. Now this was D squared, so to get rid of it I have to square root. So now D equals the square root K Q1 Q2 over F. And all of this is inside the square root. Well, now I'm ready to plug in numbers. D equals square root. K is 8.99 times 10 to the 9th. Q1 is 2.5. It says microcoulombs, so it's times 10 to the negative 6. They're both 2.5 times 10 to the negative 6, because they're both 2.5 microcoulombs, divided by the force was half a Newton. Okay? So everybody should be typing that in their calculator now. Everybody. Type it in your calculator. Show your partner. Okay. What do you get? Distance equals 0.335 meters. Now, as we've seen in previous problems, 0.335 meters is kind of an awkward unit. We're looking at electrostatic forces, so we would move that decimal 2 places back this way, and we could say 33.5 centimeters, and that would start to make a little more sense. And there we've solved Coulombs Law problems for each of the variables and learned about scientific notation, micro coulombs. Okay. At this point, you need to revisit the problems from your independent practice with the sub.